Now that we've spoken about mass, we want to talk about an important concept in physics. It's the center of mass as it relates to systems. Now, these are two particularly important words. So let's start out with system. It is a group of interacting or interrelated elements. That's important. They're interacting or interrelated elements. They act according to a set of rules to form a unified whole. So we could think of this simply as, let's say we've got these four bodies. We can kind of draw this line around it and say this is our system. They are a group, they're interrelated, they follow a set of rules, and they act as a unified whole. Now, what we might imagine is that these 4 little or 5 little or 6 or 7 or 8 little objects came from a shotgun. And that shotgun was fired, and this is buckshot. So then we might imagine that all these little particles are behaving like a system. They are related to each other. They're going to follow a set of rules together because they're all tied to the event that occurred when they were fired from that shotgun. So system. Let's go a little further with system. A system is surrounded and influenced by its environment. It's described by its boundaries. Notice in this picture with the shotgun, I drew a boundary around it and said it's just these particles. You know, the trees and the leaves and the birds flying around, they exist in the environment, but they're not part of the system as we study them. It's influenced by its environment. It's described by its boundaries, structure, purpose, and expressed in its functioning. Again, all of these particles are behaving together as a result of an event, the firing of this shotgun, and their behavior, at least so far, as we have seen it, are all related to the firing of that shotgun. That's what makes this a system. So that's the system part. What about the center of mass? Well, the center of mass, you might imagine, just from the name of the word, is probably somewhere right here. That if you took all those pieces of buckshot, that pink dot might represent the center of all of it. So let's delve into this a little bit more technically here. The center of mass of a body or system of bodies, it's a distribution of mass in space, sometimes called the balance point. Is a unique point where the weighted relative position of the distributive mass sums to 0. The way to think about this is a balance beam. You could have an object here and an object here. If these were equal in mass, you might expect that this one would fall downward. But the center of mass would be located here. And if we moved this balancing point to that location, then the seesaw would be balanced. It is the place where, when we look at all the other masses in the system, this one and this one, that if we look at the distance and the mass of this body, and the distance and the mass of this body, they serve to cancel each other out, with this being their center. In other words, this system of this mass and this mass could be replaced with this, having moved that fulcrum over. By moving that fulcrum over, we could replace it to that point. So that's what we mean by the balance point. Notice the key words they say here, the weighted relative position, that's key. Point which a force may be applied to cause a linear acceleration without an angular acceleration. In other words, if this seesaw, which is now balanced, if we were to push on this thing, push on it like so, in this direction at that point, the whole object would translate in that direction. It wouldn't spin. But you might imagine if I pushed on this in that location, since this right here is the balance point, this thing would start to spin or rotate. And that's what they're talking about there. It would cause a linear acceleration as opposed to a rotational one or angular one. And so why is this important? We can sometimes simplify things if we just treat things like a center of mass. We take our system of two bodies, combine them into one, and imagine that instead of having these two bodies, we have another body now with 2m located at that central location. This system will behave as if we replaced it with one body at the center of mass. We take the system of particles, find its center of mass, the balance point. We replace it with one mass equal to all the mass in that location, and we study this because this is easier to study than this. And that is the point of finding the center of mass and properly defining our systems. So they are simplified. It's a hypothetical point where the entire mass may be assumed to be concentrated to visualize its motion. And that's just what I described. Or it's a particle equivalent of a given object for application of Newton's laws of motion. So this is the equivalent point that if the mass were all there, this whole system would behave, this would behave the same as this system. So there's many, many different ways and instances for determining the center of mass. And as I said before, the best way to think about this is that it's the location where one object with a mass equal to the entire system could be placed. So one method is a centroid. Now this is typically something you would have learned in elementary or middle school, but probably didn't. A centroid involves a situation where it is the body has a uniform density. Uniform meaning one. So we can look at this as, let's say, an object like we have here on this Cartesian plane that has these coordinates x1, y1, and so forth for points A, B, and C. And if this is the body bounded by this triangle, if we were to, since it's uniform, draw these bisecting lines across, that point of intersection would be the center of mass because the mass is distributed uniformly throughout that space. Now, whether or not this is a uniform body like so, or we have three equal masses, one at point A, one at point B, and one at point C. Notice mass, mass, mass. The masses are equal. The center of mass would be given by that G. Now, the same would be true if we had a triangular-shaped board. If we had a triangular-shaped board and we put three equal masses on these corners and set them on top of that board, that would be the balancing point. It would be a two-dimensional seesaw like the one-dimensional one we had up here. It would be the balancing point of the masses. But this requires a uniform density, and that's what we call the centroid when we do that. Now, a plumb line method, notice that the bodies we have here are planar, lying all in a plane. What we can do is take this irregularly shaped object. It does not matter whether or not the density is evenly distributed. So the density need not be evenly distributed. And what we do is we create a pivot point. We have a plumb line, which is a string, and there is a mass, or what's called a plumb bob, put at the bottom, put on that string. And if we hold it with our fingers at this particular point, the string will go toward the center of the earth. And if we draw a line, matching where that plumb line is, and then we pick another location, anywhere on the body, attach the same string, and let the string dangle, it will form this line. Now, what's important is both the string and the object. The body and the string are free to rotate. That intersection point will be the center of mass. And no matter how many different locations we choose and do this, they will all go through that central point to help us identify the central mass. Now, of course, this is planar, it's two-dimensional, but we can then we can visualize it. A similar thing would happen if we tried to do this in three-dimension. Now, there is a formal way to calculate these things. Unfortunately for us, we're not going to have to spend much of any time calculating them. But basically, the formula is designed to create a weighted average, weighted by the mass. So what we have here is, if we have a two-body system on a line, say we have mass 1 and we have mass 2. So this is mass 1, and let's say we have our reference point. Let's make this 0. Doesn't matter where the reference point is. We have the mass of 1 and its position on that number line. Multiply those two. We multiply the distance and the position for 2. That will be equal to the total mass and its location, which we can visually see must be somewhere between these two, depending on what M1 and M2 are. But the center of mass must be between them, and using this formula, we could calculate exactly where it is. What we're doing is we're taking this position, giving it its proper weight through its mass, this other one its position, and weighting that position according to its mass. And that's how we can find that central point. So that's if we have 2. If we want to generalize this to n or any number of particles on the line, what we can do here is we can see that on this side we are taking a sum of those. So we take the sum of each mass times its distance will be equal to the total mass times its center of mass. So here is the position, the center of mass position, and here is the total mass. Here we have the total mass and the center of mass position. Now this is for 1 dimensions. We can extrapolate this to 3 dimensions, where we do the same thing independently for the x, for the y, and for the z's. Now this equation looks a little bit different, but if you notice, if we take this one up here, this is the 1 dimension, and we solve for xcm, we get the sum of mi xi all over big M. And so that's just solving for the x coordinate of the center of mass, the y coordinate of the center of mass, and the z coordinate of the center of mass. So that is a little bit of theoretical background about what center of mass is and why it's important. It is much more important that you understand what it means conceptually than to be able to calculate it in this course. In our next installment, we will look at examples of center of mass coming into play.